Good morning. Today this is review number 3, and I'm not sure how well you can read it. It looks good on my phone. This is mainly for me, just to keep me on track. But today we'll be looking at metabolism. Enzymes is kind of our overall topic. But we're looking at metabolism, energy, how energy is carried with electrons, redox reactions, not the math or anything like that, just the basic idea. Exo and endothermic reaction graphs, might remember those. Activation energy. Enzyme structure and function. How does temperature affect an enzyme? We kind of mentioned that in the previous video with denaturation. But also what happens if I increase substrate concentration or enzyme concentration. Those little brackets, that's the abbreviation for concentration in chemistry. We'll also look at inhibitors, both competitive and non-competitive. And we'll go back and look at aspirin again, how that was an example of a competitive inhibitor. We'll also look at activators, coenzymes and cofactors, and then negative feedback. Negative feedback and positive feedback loops will come back in later on in the genetics unit, but we'll give a negative feedback example here. Okay, so the first thing that we wanted to look at was metabolism. So let me go ahead and quickly shift the video over here. See if I can get it without getting that lamp in there too much. That might mess with it. Okay, move these out of the way. So what we're seeing here is I have this picture of metabolic pathways. And you might remember we referenced this in class quite a bit. So if we zoom in on it, what we'll find is there are just tons and tons of chemical reactions happening in the average cell. They do have some photosynthesis reactions in here also. So we do have a little bit of a merger of plants in here as well. But whenever I look at this, I'll notice here's some chemical, xylitol, and then there's an enzyme that runs that chemical reaction that turns it into dextroxylose. If I see that that's an ose, what do I know about it? That's right, it's a carbohydrate. When things end in all, that means they're alcohols. That usually means they have OH groups. For us in AP Bio, all kinds of crap has OH groups, so that might not actually help that much, but later on in organic chemistry, that's what that would tell me. So there's an enzyme, and I can look it up on another page, 2.7.1.53. There's an enzyme that runs that chemical reaction, that speeds that chemical reaction up. So enzymes always speed up chemical reactions. These are major metabolic reactions that happen in us. So I can scroll left, I can scroll right, just tons and tons of crap that happens. The idea is that if an enzyme runs this chemical reaction that converts this molecule into this molecule, that enzyme, if it runs that reaction, as long as that enzyme is working and it's in the proper concentration, if that reaction is needed for life, it eventually makes histidine. That's one of the amino acids. So that is essential for life to make this non-essential amino acid. All right, so if that enzyme is misfolded or something, if it's mutated, then now that chemical reaction doesn't happen. So that could be catastrophic, or it could be no big deal. In this case, it looks like it's going to be a big deal, unless we have an alternate way of making histidine, for example. Okay, so whenever we talk about metabolism, we're just talking about all these major chemical reactions that are happening inside of our body. And I'm going to go ahead, there's a reaction we're going to look at later right there. So I'm going to go ahead and center that on the screen. And then let me go back and fix the camera. All right. Not the most professional videos in the world, but I am doing my best. Okay, so metabolism is made out of two parts. Anabolic reactions and catabolic reactions. So a lot of times students will mistakenly say, if I ask them what enzymes do, they'll say they break things down. Well, that's true, catabolism, catabolic reactions, catastrophe, breaking down, but they also build up. So if I eat some almonds, there's protein in almonds. One serving of almonds has 6 grams of protein. Well, this is not muscle, it's plant material, it's almond. But if I eat these, whenever I eat these almonds, the protein inside, there's other stuff inside, But the protein inside is made out of chains of amino acids. It's a polymer of amino acids. Protein is a polymer of the monomer amino acids. And let's say that this purple, brown, green, orange, red, this is the protein in almond, whatever proteins are in there. I don't know what the proteins are called in almonds. Okay, like if it was an egg, it might be albumin protein, but in almonds, I have no idea. So I can eat this. Once again, the illusion. Oh wait, need to go on the other side. I'll just keep that in there. I've got another meeting coming up before too long, so I don't have time to reshoot this. So I'll just have to look like an idiot. That's what you get. So this is almond, purple, brown, green, orange, red. So when I digest it, I chemically break these chains of amino acids down. That's a metabolic reaction. Catabolism, it's a catabolic reaction. Again, it's where we get the word catastrophe, to break down. And now, what my body can do is, we'll learn about molecular genetics, or we'll review molecular genetics in a future review video. But now what I do is I take these amino acids and I just rearrange them in a different order. So now if I go green, purple, brown, red, orange, that might be human muscle. And if I worked out, then my body will use this to build more muscle. If I worked out my legs or whatever, then my body will go in and repair my leg muscle, and when it does, it'll add more muscle fibers if I was lifting heavy enough. So essentially you're just rearranging the letters. So like the order of amino acids matter when it comes to a protein. The example that I've used in class many times, I know you guys are tired of it, but rat, R-A-T, tar, T-A-R, art, A-R-T. I can take the same three letters, scramble them, and they have totally different meanings. So I can take the same group of 20 amino acids, put them in various orders, various combinations, double sum, triple sum, leave off sum, and I can have all the different amino acids. You know, we have an English alphabet of 26 letters. Based on which letters I use and what order they're in, that determines the meaning of the word. Same thing with enzymes. Whenever I put the amino acids in the correct order, it's correct, and I can run this chemical reaction. But if I put them in the wrong order, or maybe I have a mutation, and now instead of it being purple, green, brown, now it's purple, red, brown. Well, that might not be able to run that chemical reaction anymore. So if my DNA is incorrect, it'll code for the incorrect order of amino acids. I'll now have the incorrect protein with the incorrect shape, possibly, and so now I might not be able to run that chemical reaction. That's how most mutations manifest themselves. An error in the DNA, which means an error in the RNA, which means an error in the order of amino acids, and now my protein is messed up. I've kind of changed the shape of my lock and my key. Remember how enzymes fit substrates, kind of like a lock and a key. So we, or an induced fit model. Okay, so metabolism, anabolic is building up, like anabolic steroids. If I was taking anabolic steroids, I'm trying to bulk up. I'm not trying to like trim down. The next thing that we wanted to look at was energy and electrons. So how is it that I get energy out of food, whereas I don't get energy out of this pen cap, or out of this string right here? So I can eat the string, meaning you can eat whatever the heck you want, doesn't mean you should. So I can eat the string, but then I'm just gonna like poop out string. So I can't chemically break down string or a piece of plastic because I don't have an enzyme for it. But the reason that almonds give me energy is because I can steal electrons from almonds. So here's the part that's kind of interesting. Food contains energy. In biology, we measure energy in calories. I think the chemistry definition is like how much energy it takes to raise 1 milliliter of water, 1 degree Celsius or something like that is, no, that's specific heat. Anyway, a calorie is a measure of energy. If we were in a physics class, we might measure energy in joules or something like that. So, but a calorie is just a way that we measure energy. Okay, so how is it that I get calories, energy, out of food? Well, the way that it works is, let's say I've got a nucleus right here with an X, and I have energy levels. Your teacher might have called them electron shells or something. If I had a periodic table, pretend there's a periodic table right here, row 1 would be like hydrogen, a whole lot of nothing, helium. And so that means that my first ring has 2 electrons. It can hold up to 2 electrons. If I look at row 2, I'll have 2 elements, a giant space, and then 6 elements. So row 2 has, row 1 was hydrogen, helium, 1, 2. Row 2 has 1, 2, 3, 4, 5, 6, 7, 8 over here on my periodic table. So that's why the second level can hold 8. Okay, so this is a little bit simplified, but the way that we get energy from food is by stealing electrons from food and then dropping those electrons in energy levels. So let's say I've got on kind of a dark shirt, or I've got a vehicle outside that's painted black. If I go out there and it's in the sun, then that black painted car or my dark shirt is going to feel warm. And the reason for that is sunlight is hitting whatever pigment is in there that's causing it to be black. Actually, I guess if it's black, it's not reflecting anything. But whatever is in the black paint that's absorbing everything, it's absorbing that energy. My white shirt is reflecting most of it. So that's why my white shirt will be cooler. My dark shirt will be warmer because it's better at absorbing energy than my white shirt. Well, how's my dark shirt absorbing more energy or my white shirt reflecting more energy? What will happen is as the sun, here's the sun, as the sun shines down and it hits electrons, let's say I've got a few electrons right here, those electrons are excited and they go up to the next energy level. So if the sun is hitting, let's say, that electron right there, then that electron might go up in energy levels if it absorbs energy from the sunlight. It might go up another energy level. So there you go, the electron that was here now moves all the way up to here, and we say it's excited. In chemistry, that's the actual term. So these electrons are excited to higher energy levels, but they're not stable up there. Again, from chemistry, you might remember that level 1, kind of like I was showing you on my pretend periodic table, contains 2 electrons. Level 3 can hold 8, and so forth. So I'm supposed to fill up level 2 before I can have anybody in level 3 or level 4. So those electrons are not stable up there. So they immediately fall back down. Kind of like, here's an expo pin. It's not stable up here. So if I raise it up a few feet off of this bench and then I let go, it'll fall back down. That's what I'm doing. Sunlight zaps these. Electrons absorb energy. They go up in energy levels. They're not stable, so they fall back down. Once they fall back down, they release energy. Just like as this falls back down, it can release energy. You might, depending on the microphone, even be able to hear it. Energy of motion is converted. It's got like 2 feet worth of potential energy. Now it turns into kinetic, more kinetic, more kinetic, and then sound. So that's how we actually get electrons to go up and down. Whenever they're falling, they're releasing energy. Okay, well, what does that have to do with food? That's telling me why my dark shirt feels hot and my white shirt doesn't. My white shirt, for whatever reason, is reflecting most of the energy from the sun. Well, how does that affect food? Well, let's say that somewhere in my body, like, I don't know, maybe in my mitochondria, our next set of videos will actually get into cellular respiration and mitochondria, so this is also a preview of where we're going. What if I had some proteins, like proton pumps, in the electron transport chain that were located in my mitochondria, and they had some electrons? So right there, I have some molecules, and they've got some electrons. There you go, there you go, there you go, there you go. Okay, what if I could eat some almonds, steal electrons from those almonds? So part of the digestive process is I steal electrons from those almonds, and what if I could, like, let's say that this green one up here now is food. What if I could steal some electrons from energy level 3 and then hand them off to this guy at energy level 3? That means this guy just gained an electron, but energy level 2 is not full. So what's immediately going to happen as soon as this is supposed to be an arrow, as soon as I transfer this electron from a piece of food, my almonds, over to my mitochondria, once I transfer it over there with an electron carrier like NADH, then that electron's immediately going to fall. Well, as it falls, what does it release? Energy. So that's how we get energy from food. I steal electrons from food, at higher energy levels, and then when I accept them, they're not stable at those energy levels, so they fall down. I then use that energy of falling electrons to eventually create ATP, generate ATP. And we'll look at that in future videos. So that's how electrons actually help us carry energy. Exo and endothermic graphs. So you've probably studied this in chemistry and biology now. Oops, that's the exact same graph. Here we go. In this, let's say I have time down here, and I'm not going to worry about units. And over here I have energy. Same thing, it's probably in like calories. Energy, title. Okay, which of these is exothermic and which of these is endothermic? Exothermic, thermic, temperature, thermometer, thermos. Exo, exiting. So energy in the form of heat is exiting. So this one over here is exothermic because I start with a certain amount of energy, maybe 80. And over here, I start with a certain amount of energy, maybe 20. So whenever I do that, then I will notice that I start the chemical reaction at the beginning with 80 units of energy. I run the chemical reaction and I end at maybe 20 units of energy. So that means I release 60 units to the environment. So 60 units exited, so exothermic. 60 calories, that's a lot. Over here, kilocalories technically since it's a capital C. Over here, same thing in reverse. Here I'm absorbing 60 calories worth of energy. So which one of these would feel warm, which one would feel cold? Would this one over here feel warm or cold? It's going to feel cold because it's sucking in energy from the environment. So if I take chemical A and chemical B, throw them in a beaker, and they now mix together, if they start absorbing energy from outside, if I touch it with my hand, if I'm holding it with my hand and they are sucking in 60 calories worth of energy, they're sucking that energy in from me. If it's just sitting here on the counter, they're sucking it in from the room, the heat of the room. And so right now, chemical A and B are in there. So here's chemical A. A plus B makes C, let's say. They're going like this, and whenever they do that, they are sucking in energy. So they mix in, they suck in energy from the room. If I touch it, they're sucking in heat energy from me, and so I'd say it feels cold. When heat leaves me, I feel cooler. Then the reverse is true over here. This is releasing energy, so that's exothermic. That's like those hand warmers, the iron plus oxidizer hand warmers that you might get at Walmart or something. This is like the ice pack. It's not really ice, but we call them an ice pack. You twist your ankle, your coach kind of has the little plastic thing, breaks it open, and then the slushy stuff starts to turn cool. You can test this reaction at home if you mix baking soda and vinegar in a Ziploc bag, kind of like you know how it will bubble and fizz. Well, if you put it in a Ziploc bag and feel it, you'll also notice that it feels cold. So that's an endothermic reaction. These, burn something, that's exothermic. Okay, so enzyme structure and function. Whenever I start looking at these graphs, it relates to their structure and function. This part right here, that bump is called what? Activation energy, yeah. Or energy of activation. And that's the amount of energy that it takes to make this chemical reaction go. So let's say this is 100. That means if I started off and I have a chemical reaction of this, C, and I'm going to break it apart, then whenever I want to run the reaction, I have to input 20 units of energy. I have to make it from 80 up to 100. I have to input that much energy to make the reaction go. And the example that I gave in classes for this was, let's say that I had a piece of paper and I had a flame, like a lighter or something. Can that lighter set this piece of paper on fire? Well, sure, but if I go like this, the paper doesn't catch on fire because it doesn't have enough time. That's because when I go like this, the paper maybe absorbs a couple of units of energy, not 20, so I don't turn into charred, burnt stuff. If I go slowly enough, then now I go, here's me absorbing energy. I've absorbed 0 energy. 0, 0, 2, 4, 6, 8, 10, 18, 20. Okay, as soon as I hit 20, as soon as I absorb 20 units of energy, now this catches on fire and it starts releasing heat. Okay, so what does this have to do with enzymes? We said that enzymes always speed up chemical reactions. They might be anabolic or catabolic, but they always speed up chemical reactions. How do they do that? They lower activation energy. So now, if I add an enzyme, my chemical reaction looks like that. So now instead of having to input 20 units of energy, I have to input 1 unit of energy. So now this reaction would happen 20 times faster. You might remember the fastest enzyme that I know of that they've timed was carboxylane hydrase or alcohol dehydrogenase. I think it was carboxylane hydrase. That might be it. The one that's converting CO2 between your lungs and your bloodstream. But carboxyl, I'll have to double check it. But it increased the rate of reaction by 10 million times. That means it lowered the activation energy by 10 million times. Carbonic anhydrase, that's what I was looking for. I'll have to, again, just live without that edit in there also, carbonic anhydrase. And so I can lower this a lot. So when you say enzymes speed up chemical reactions, they don't speed it up like 1 time or 2 times or 3 times. It's typically thousands of times. Or the super fast ones, millions of times. That's pretty crazy. Now, if I've got these graphs, over here I've got an enzyme. Remember from the last video, primary structure, secondary structure, tertiary, all that. So I might have an enzyme that looks like this. So it has primary, secondary, and tertiary structure. Well, the way that enzymes speed up chemical reactions is by stressing chemical bonds. And what I mean by that is this. Let's say that this enzyme has a bunch of positives on one side, positive amino acids on one side, and a bunch of negatives on the other. Well, if my substrate is shaped like this, that's supposed to fit my enzyme perfectly. So if my substrate looks like this, then now, when that substrate is in there, it's actually stressing the bonds because this side of the substrate has a bunch of negatives, this side has positives. So the positives in my enzyme, or my positives will match up with the enzyme and the negatives will match up with the enzyme. And so now I'm pulling on those bonds. It's kind of like this. Here's a piece of paper, let's say. There you go. Here's a piece of paper. Here's how much energy it takes to tear it. Okay. But if I put this substrate into an enzyme, the enzyme's pulling it this way and pulling it this way. Now how much energy would you have to input to tear it if I'm stressing those chemical bonds? A whole lot less. So that's how stressing chemical bonds actually makes chemical reactions go faster. So what's happening there is this right here. So I need the right chemical and physical fit. This has to physically fit, kind of like a cookie cutter, but it also has to chemically fit. Positives and negatives have to be in the right spot to stress chemical bonds. I can also set up things to where maybe this is floating around, this is floating around, and as long as I can get them together, they'll stick. So that's how I might be able to join things together. Almost like if I had a magnet and they're flying around the room, they might not ever get a chance to actually stick. But if I could grab one with my enzyme and grab the other with my enzyme and hold them close to each other, now they have a shot at actually sticking. If I increase the substrate, how fast? So this is an exothermic reaction. Now I'm looking at like product, totally different graph, product over time. The labels on your axes are important. On the real test, you'd also want to put units of time and units of product in a title. So when I add more substrate, then chemical reactions can happen faster. If I'm basically an enzyme in the room, I'm not used up, and these expopens are flying around, so this is expopenase, then these expopens are flying around. If there's one in the room, it'll be a while before I finally bump into it and break it down. If there's 2 in the room, I should be breaking down pins twice as fast. If there's 100, 1,000, 1,000,000 in the room, So the more substrate I have, the faster I can produce products until I'm saturated. At some point, I can't go any faster. So if you keep adding more and more and more and more substrates, then I break down more and more and more and more. But once there's 1 billion pins in the room, 5 billion pins in the room, 10 billion pins in the room, it doesn't matter. Like, as quick as I can grab and break down is the limiting factor. So at some point, my reaction rate, if this said reaction rate, will level off. At some point, I'll convert, so let's say that that was reaction rate. At some point, I'm going to quit producing product because I basically broke down all the expo pins. So always study what your graphs are showing. My reaction rate will level off at the end, and my product can level off at the end just because like I'm running out of stuff. I don't have any new product. Or my reaction rate just kind of like hits a straight line because I can't go any faster. Let's see. Next up, inhibitors, activators, coenzymes, and feedback. Okay, so we'll get on to. With an inhibitor, we could stop some chemical reactions from happening. So the example that I gave in class was there are enzymes in my cells that store energy as fat. But then there are also enzymes in those same cells that say, hey, this guy hasn't eaten in a while, so let's release the energy from that fat. So when I eat excess at meals, I might store energy as fat. There are enzymes that help me convert my food energy into fat. If I haven't eaten in 12 hours, then my body will say, hey, let's access that fat and start breaking it down and converting it back into like ATP, for example. So I need enzymes that sort of like build up fat and enzymes that break down fat in the same cell. Would it make sense to have both of those enzymes running at the exact same time? No. So I need to be able to turn enzymes off whenever I want with inhibitors. And the way that that will work is I have competitive and non-competitive inhibitors. So here's an enzyme. And maybe it fits this substrate. That's my original substrate. Well, I might also have an enzyme, chemical, that looks like that. That's supposed to be the same shape, except it's obviously a different chemical. So that inhibitor can compete for the exact same spot as that substrate. Remember, the spot inside of the enzyme that is the place where action happens is called the active site. So the substrate fits into the active site. That inhibitor can also fit into the active site. So now the inhibitor is getting in the way of me grabbing the real substrate. It's almost like if I had a lock, the enzyme, and my key is the substrate. If I'm supposed to have my real key go in there, then I can, unlock the door. But if I have just some other key that's close in shape, but it doesn't open the door, if it's in there, then now my original substrate is kind of being outcompeted for the spot. So that's competitive inhibition because that inhibitor is competing for the same parking place as this substrate is. Non-competitive looks a little bit different. Non-competitive is when I have an enzyme with a different an allosteric site. Yes, it still has an active site. That's where the substrate's supposed to go. But now my inhibitor can bind at an alternate site, an allosteric site. Whenever that happens, you're like, well, can't my substrate still fit in there? No. Because what we'll do is whenever this enzyme is on its own, it's stable in that shape. Whenever I add the inhibitor, now its chemical stable shape is different. And so now, maybe, we see that. So now my substrate can't fit. It's sort of like this. Let's say this is my enzyme. And this guy right here is my substrate. So here's my enzyme. My substrate fits in there perfectly. Great. But it turns out over here I have an allosteric site. And whenever this inhibitor, orange, hits this allosteric site, then now, watch this. It changed shape, right? So even though this chemical is binding here, it can have an effect on bonds far away. So that's how a non-competitive inhibitor binding to an allosteric site can change the shape of my enzyme. What happens if I remove the inhibitor? Everything goes back the way it was, and now the enzyme is back on. Enzyme is on, changes shape, enzyme is off, remove it, goes back to its normal shape. You might remember my analogy of a backpack. How about that? The backpack's right here. This is how I stand. Put a backpack on me, pretend that this one's really heavy, and now with this is how I stand. We call this a conformational change, right? It's reversible. Take the backpack off, I straighten back up. Put the backpack on, like that. That's exactly what's happening with the enzyme. Add the inhibitor, remove it, and you're changing the shape of the enzyme. A conformational change. I did have an example of competitive inhibition that I wanted to remind you guys of. We saw it earlier in the year with aspirin. How is it that aspirin makes my headache go away or kind of relieves the throbbing pain? How is it that grandpa can take a baby aspirin and it's supposed to like thin his blood? How does that work? Well, it works with this reaction right over here. So I have this chemical called arachidinate. Hope I'm saying it right. And there's an enzyme, a couple of enzymes that run the reaction that convert that and convert it into prostaglandin. Prostaglandin is then converted into thromboxane. So prostaglandin, the job of that is it causes kind of like irritation. It's responsible for the throbbing pain of a headache. It's kind of like the pain of if I have a paper cut, that's a sharp pain. But if I like smash my hand in a door, that's a throbbing pain. So prostaglandin is responsible for that. Thrombo, if you had like medical terminology or something, that's blood clotting. A thrombosis, a deep vein thrombosis, a deep vein blood clot. That's why on international flights you're supposed to walk around. So what aspirin does is it inhibits this reaction. I want to double check to make sure you guys can see when I'm pointing on the screen. So what will happen is aspirin is inhibiting one of these enzymes right here. I haven't looked up the number. So now I don't make prostaglandin, so now I don't have that throbbing pain, and my blood is quote unquote thinner. It doesn't clot as easily. Thromboxane is responsible for helping my blood clot. It's part of the clotting cascade. So how is it that we actually inhibit this with aspirin? The model that we have looks like this. And again, I want to double check to make sure you can see that okay. Go a little bit closer. I apologize for the lack of professionalism in my videos. So what we have is this green right here is the enzyme. It's in a phospholipid bilayer. And arachidonic acid or arachidinate, I hope I'm saying those right, are the same thing. Arachidonic acid just means that like technically on arachidonic acid at the end it'll have a C, I think you can still see this, C double bond O, OH, carboxylic acid. Whenever it's arachidonic acid it looks like that. When it's arachidinate, it gave up its hydrogen ion. A hydrogen ion is a proton. I'll explain that in the next video. But an acid is an acid because it's good at giving up protons. It's good at giving up hydrogen ions. A hydrogen ion, again, is a proton. So they're the same thing. It's just, have you given up your proton or not? So arachidonic acid has COOH. Arachidinate has COO-. So for AB Bio, that doesn't matter. I'm just, if you're watching the video and you're like, wait, that's a different chemical, it's essentially the same. So what normally happens is this. If arachidonic acid goes into this catalytic site of the enzyme, the active site, there's also one here, then we now catalyze the reactions to make prostaglandin and thromboxane, and I'll feel pain and my blood will clot more easily. My platelets will be activated, which makes sense because if I smash my hand, I need to tell my brain, don't do that again, feel pain, but also if I smash my hand, I probably need to increase blood clotting because I'm probably bleeding. A bruise, for example. After aspirin, what aspirin does is it'll go in and add an acetyl group up here. So it goes in and part of the aspirin is left behind. So here's aspirin, here's the acetyl group. You might remember acetyl groups, we mentioned those in histone acetylation epigenetics. To help turn DNA on, we add acetyl groups to histones, for example. So aspirin, acetyl salicylic acid, will enter the enzyme's active site, drop off its acetyl group. Now, it turns out that arachidonic acid can't fit in there. There's just not room. We had a little cleft that was this big, and it's supposed to fit this. But if I go in and I add an acetyl group, now I can't fit this. So the aspirin is basically just taking up space. It's an inhibitor competing for the active site, so it's a competitive inhibitor. So that's actually how aspirin works, which is pretty cool if you ask me. The last thing, let me zoom back out. The last thing we were concerned with was negative feedback, which we might not get to based on time, we'll see. But activators, coenzymes, and cofactors. Activators basically are the reverse of inhibitors. Inhibitors take enzymes that are on and they block and turn them off. An activator would work the opposite. For example, this allosteric inhibitor is turning this enzyme off. An allosteric activator would be, here's an enzyme that's off. Whenever the activator binds to it, now it's in the on position. So same idea, you're just turning on versus turning off. Coenzymes and cofactors, commonly vitamins are coenzymes, like coenzyme A is vitamin A, or vitamin C is a coenzyme also. And the way that those work is essential that we have vitamin C if we want to avoid scurvy, which means we'll have crappy collagen, which means our connective tissue will be bad, ligaments and tendons are bad. The only thing that's holding your tooth in really is a ligament. So whenever you have a loose tooth when you're a kid, that little thing that you finally have to like snap to get your tooth to kind of come out, that's a ligament. If you have scurvy, those ligaments suck because your collagen is not very good. It has a low melting point. And so because of that, your teeth fall out on their own anyway. So here's an enzyme, and here's a substrate. So does that substrate perfectly fit that active site? No. That's why we need a coenzyme, cooperate, like vitamin C or whatever. And now, with this, I'm kind of sealing up the active site. Now that enzyme can run a chemical reaction. Sometimes the vitamins or minerals or whatever, if it's a cofactor, will add a chemical on here. They'll add a chemical onto the enzyme that helps them do their job. But cofactors and coenzymes are essentially the same thing. Technically, and this is beyond AB Bio, but technically a cofactor is inorganic, a coenzyme is organic. So if you're talking about some sort of ion that's inorganic or whatever, then you'll be like, it's a cofactor. But if you're talking about like vitamin A, well, that's a coenzyme. Same idea, they just have slightly different names. Looks like we do have time for negative feedback really quick. So here's an example of negative feedback. Let me adjust the camera again. Okay, on this what we're seeing is the final product is feeding backwards and turning off the generation of the product. So here, I've got several enzymes, enzyme 1, 2, 3, 4, and 5. They basically take this chemical, threonine, and they tweak it again, and the final product is isoleucine. That's an amino acid. And so then what will happen is isoleucine can turn off the enzyme that helps make isoleucine. So what that means is we'll always have a steady amount of isoleucine. The best example of that is like our body temperature or a thermostat. With a thermostat, pretend that I have this little box right here. That's where I like type in the temperature. Pretend that that box makes the heat. I want to heat up the house. So let me zoom back out. Just a little bit. So let's say I want to heat up the house. I want the house to be 75, but it's currently 70. All right, so yeah, good. So we're currently at 70. So that device will sense that it's 70 and say, make more heat, make more heat, make more heat, make more heat, make more heat. Once I get to 75, the heat tells the thermostat to quit making heat. So the thermostat, we're pretending, made heat. So here's my thermostat box. Pretend that it makes heat. I know it doesn't. There are other structures that do. This is just like, the brain of the system. But I say heat it up to 75 and it says make more heat, 71, more, 72, not enough, more, 73, 74, 75. Then heat feeds back and tells this, hey, we're at 75. So what does this thermostat do? It says quit it. Now, if it's winter, the room's going to cool off. It goes down to 74. This guy will sense that. He'll get that feedback. And so now we turn it back on until it gets to 75, turn it off. 74, turn it back on. So we always stay at a steady 74, 75. Usually whenever you do negative feedback, you maintain a pretty steady state. My blood sugar should always be pretty steady. I don't want it to drop to 10. I don't want it to increase above a couple hundred. So I always want to keep it at, let's say my fasting blood sugar should be maybe 85, 90, 95, somewhere in there. So I want to keep a pretty steady state. So negative feedback looks like a steady state. And again, we'll come back to feedback again with molecular genetics later. All right, I've got my first of many Zoom meetings, so I've got to bail for now. Thank you guys.